Okay, so next presenter is Marius Langwasser. He's going to talk about enhanced grid frequency support by means of HVDC-based load control. Marius Langwasser received his bachelor and master degrees in electrical engineering and business administration at Kiel University in Kiel, Germany. Since 2016, he is scientific staff member and PhD student at the chair of power electronics at the Kiel University, and is responsible for the Copernicus project ENSURE. His current research interests include control and protection of hybrid grids and ancillary service provision with HVDC and smart transformers. Thank you, Marius, for joining. The stage is yours to present.
Thank you. I hope you can see the presentation.
Yes, we can. Thank you.
Great. Good morning, ladies and gentlemen. Bon dia a todos. My name is Marius Langwasser. I'm from the chair of power electronics at Kiel University in Germany. And today I will speak about the enhanced grid frequency support by means of HVDC-based load control. The replacement of the conventional generation by the renewable ones has led to significantly reduced system inertia due to the power electronic interface of the renewable generation, which does not provide any rotational inertia to the grid. So as example, in Germany, it is expected that the equivalent inertia would drop from around 6 seconds down to 3 or 4 seconds. In this scenario, the two major frequency incidents, which happened in the year 2019 in Europe and in the UK, call for faster frequency regulation. The HVDC systems, both the point-to-point and the multi-terminal ones, can support the conventional primary frequency regulation of the synchronous generators. However, this can be done with higher dynamics. There exist still limitations of this approach of conventional primary frequency regulation with the HVDC system, which are that this support can only increase the system damping, but does not provide any inertia support. And the second one, which is probably the most important one, is that large frequency deviations occur in the supporting areas, which can go up to 500 millihertz. As solutions in this work, we are presenting an inertia emulation strategy. So this is done basically by adding derivative terms in the power controller as presented already in the literature. And then the core of the paper, HVDC-based control of voltage-dependent loads to solve the problem with large frequency deviations in the supporting area. The conventional HVDC-based primary frequency regulation is based on an external group controller, which adapts linearly the power reference from its original market set point following the linear characteristic after the frequency deviation. The virtual inertia emulation, as I already introduced in the first slide, is based on a derivative term, so it's proportional to the frequency derivative, and this gain is selected then to obtain the desired emulated inertia. Now we are coming to the HVDC-based control of voltage-dependent loads. On the top, you can see the algorithms implementation in the time frame with respect to the conventional primary and secondary frequency regulation of the generators. The first step is a periodic load sensitivity identification in real time. This is important also that it is repeated within a certain small time steps of several minutes maybe, because in that case we can react on the load dependence on weather, season, or daytime. So this is usually referred as the loading condition. In this case, we can guarantee always an accurate control action afterwards. This identification is performed with controlled voltage variation, so small grid voltage variation, and then following measurements of the active power and voltage of the loads. In the table on the bottom, you can see some real grid load sensitivities for the high voltage grid, which are obtained in the literature from measurements or industry surveys. The second step is then the control of the voltage-dependent loads itself. So we are controlling the power consumption of nearby voltage-dependent loads through controlled grid voltage variation. This grid voltage variation is performed with reactive power injection. In general, we have to say that this support is restricted to maybe 10 seconds, so it won't interfere with any recovery of the load. As additional safety measures, we are introducing as first frequency deadband of around 100 millihertz to prevent the controller from acting in small deviations. So in the case where the frequency is just oscillating around the nominal value and no real frequency incident is discovered. And as a second measure, the voltage limitation. So we are restricting the voltage variation in the grid according to the technical requirements for the grid connection of HVDC system to a few percent around the nominal value. In this paper, the load control is implemented in the slave terminals of the multi-terminal HVDC system. So for simplicity, we are assuming the master-slave control of the multi-terminal HVDC system. However, the implementation of primary frequency regulation and inertia emulation has been already demonstrated in the literature also for droop control systems. The following analysis is based on a simplified yet sufficiently accurate model of a three-area multi-terminal HVDC system. And this will be used now for the analytical demonstration. On the top, you can see the results for the conventional primary frequency regulation of HVDC systems. In the dotted lines, you can see the case where no support is given. In the dashed lines, it's the primary frequency regulation. One can see that the positive effect of this control is that the frequency nadir in the faulty area 1 in the blue line is limited. However, no inertia contribution and hence no improvements of the rate of change frequency are visible. And as demonstrated by the red and the green lines, large frequency deviations occur in the supporting areas 2 and 3. In the middle, the inertia emulation leads to a Rokov improvement, in this case of up to 0.15 Hertz per second. However, this further deteriorates the frequency deviations in the supporting areas 2 and 3. So the first issue could be solved, but not the second one. Instead, the HVDC-based frequency support controlling voltage-dependent loads could, in this analysis, ideally compensate because it's a linear analysis, but in general could compensate the power imbalance in supporting areas. While the same frequency support, so both primary frequency regulation and inertia emulation is given to the faulty area. This control involves the small variation of the grid voltage. So this may conflict with the voltage constraints given by the system operator. And in the multi-terminal system, this leaves room for optimization. So we can optimally share the frequency support to guarantee the compliance with the voltage limits. This is the optimization. As optimization goes, we have that the same frequency support is given to the faulty area with the smallest voltage variation and smallest frequency variation in the supporting areas. The mathematical constraints resulting from these two goals are that the grid voltage variations in all supporting areas is equal, because in that case, we can guarantee the overall minimum of the voltage variation. Second constraint is that the proportional shares of, in this case, the two, or in general, of all areas that participate in the frequency support must sum up to 1, so to the total requested support. So this guarantees that the same frequency support is given to the faulty areas. From this, we can calculate that the optimal shares, so the optimal sharing of the frequency support depends on the beforehand estimated grid voltage sensitivity. And so using this optimization approach results in the case that the areas with the highest sensitivity takes the highest part of the frequency support in a grid voltage variation minimization. And also this leads to a reduced need for reactive power. So we can also limit the converter injection of reactive power. In the following, we are going to validate these analytical findings with the simulation results of the multi-terminal modified version of the Kundur benchmark. This is easy to reproduce and easy to compare with the analytical findings. So that's why we have used such a simplified benchmark model. The test cases we are using is case A, no frequency support is given. In the second case, we are adding the primary frequency regulation. In the third case, the inertia emulation is added. And afterwards, we're adding the control of voltage dependent loads. First, just one area which has low load sensitivity, then one area with high load sensitivity. Then the two areas are involved and the equal share among them is chosen. And afterwards, it's the optimized sharing, so where we are taking into account the estimated load sensitivity. On the top left, you could see the HVDC-based, the conventional HVDC-based primary frequency regulation. The limitations, which we already got in the analysis, could be confirmed also with the simulation. So we could see that the supporting areas in green and red experience the voltage, experience the frequency deviation, sorry, in case they are supporting the grid frequency in the area 1. And no improvement of the rock-off is visible. In the case in the bottom left, we could see the effect of the inertia emulation that improves the rock-off and also slightly improves the nadir already. On the right, we could see the effects of the application of the voltage-dependent loads. In this case, an Equisharing is assumed. And we can see that the frequency deviation in the supporting areas is reduced, not ideally, but almost to 0. And this guarantees, as the power is not taken anymore from generators of the supporting areas, but from the load, the reduction of the transient generator power and hence allows for smoother governor control action. In general, it is good for the support if we are using multiple terminals which should cooperate in the frequency support, because this could help to avoid unnecessary large frequency deviations, even if we are applying the voltage-based load control, the control of voltage-dependent loads. But why is it now necessary to optimize this sharing? So we compare the case with the Equisharing with the red lines and the optimized sharing with the green lines. In the case that we have the Equisharing, the same amount of load power is drawn from every area. This leads, in the case that the sensitivity of the load deviates among the areas, to unnecessary large voltage variations in those areas that show a low load sensitivity. Instead, the optimized sharing results in the fact that the high amount of power is drawn from high sensitive loads, and this leads then to the same level of load voltage variation in all areas, and this is then the minimized load voltage variation. And also a lower reactive power injection from the HVDC system can be obtained with this optimization approach. As last study case, we are investigating a stricter voltage constraint in the system. In this case, the 2.5% is assumed as maximum allowed voltage variation. With the Equishare, we can see that the voltage constraint does not generally hinder the performance of the control of voltage-dependent loads. However, a limited frequency support in the faulty area might be the result. Instead, with the optimal share, which can be seen in the plot on the bottom right, we can guarantee the full frequency support in the faulty area, even with the application of a stricter voltage constraint. We can guarantee the compliance with local voltage constraints set by the system operator, and we can guarantee the compliance with the terminal converter and capacity limits. So these three benefits can be obtained with the optimal sharing of the frequency support, considering the estimated load sensitivity. Let us conclude the work. So the conventional HVDC-based primary frequency regulation is limited by two factors. First, it only increases the system damping, so no inertia support is given to the faulty system. And the one that we are tackling as a main point in this paper is that large frequency deviations occur in the supporting areas just for providing the support to the faulty area. As solution, this paper proposes the combined use of the primary frequency regulation, inertia emulation, and the control of voltage-dependent loads to guarantee that the power is not drawn from the generators, which would cause the frequency deviation, but from nearby voltage-dependent loads. To avoid large frequency deviations, unnecessary large frequency deviations in the supporting areas, even if we are applying the control of voltage-dependent loads, multiple terminals should cooperate in the frequency support if we are having a multi-terminal HVDC system. And this calls for optimization of this sharing among the terminals. And we're proposing in this paper an optimized sharing of this frequency support among the multiple areas of the HVDC system, depending on the estimated load voltage sensitivity. Because in this case, we can ensure that we have the same frequency support in the faulty area, we have minimized frequency deviations in the supporting areas, and we have the total minimum grid voltage variation or grid voltage disturbance in the supporting areas, and also a minimum amount of reactive power that is injected in the grid by the HVDC system. Thank you for your attention, and I'm happy to answer your questions.
Thanks a lot, Marius, for the presentation and for staying perfectly on time. We already have two questions in the question and answer panel. Would you mind reading them aloud so that they get recorded and addressing them?
No, I will try here. Okay. The first question, thank you. It is the question why we are neglecting the frequency response of the load and only consider it as voltage dependent. So I think you referred to the frequency dependence of the load, so that also when we are having a frequency disturbance in the grid, or either by default or by the control, that the loads will also react on this by adjusting their power consumption accordingly. Basically, this was neglected in this paper as we are, or in the analysis, let's say, because we are not acting on the frequency itself by the control. What we have assumed in the simulation is the frequency dependence of 1, so a linear dependence of the load active power to frequency in the simulations in the PSCAT. So this, I hope this answers the question. The second question is, what is the control you're using for the HVDC? It may be interesting since the HVDC controls have influence on voltage sustaining. The control that we have used in this paper for the HVDC is the master-slave control, so that one terminal controls the DC voltage and the other control the active power exchange with the AC grid. And in general, we are controlling then the reactive power independently of the active power or DC voltage. In the case we are using the control of the voltage dependent load. We are switching from the reactive power controller to a AC voltage controller, which is set on top of the reactive power controller, to basically give the set point for the reactive power controller. Are there any other questions? In case not, and also the video will be recorded, so you would have the chance to ask me afterwards. You can find my contact details in the presentation. So my email address is there, and you could write me an email, and I'm happy to answer your question also after the presentation. Thank you.